Hello and welcome to the Sleepy Physicist. I'm so glad you're here tonight, whether you're settling into bed, curled up on the couch with a warm drink, or simply trying to wind down after a long day of existing in this beautifully complex universe we call home. You've come to the right place for a gentle journey through one of physics' most mind-bending thought experiments. Tonight, we're exploring something that should, by all rights, be impossible. Something so fundamentally catastrophic that even imagining it feels like breaking the rules of reality itself. But here's the thing about physics. It doesn't care about our comfort zones. It simply describes what would happen if the unthinkable occurred. So let me ask you this. What if gravity just stopped working tomorrow? Not gradually, not partially, but completely. One moment you're sitting there, held gently to your chair by forces you never think about. And the next moment would be unlike anything in the 4.5 billion year history of our planet. Before we begin this quiet exploration into cosmic catastrophe, if you find these slow journeys through the wonders and terrors of physics helpful for your evening routine, I'd be grateful if you tap the like button or subscribe to the channel. It helps other curious souls find their way here, and it tells me that these gentle wanderings through the universe resonate with you. Now, I should mention that what we're about to discuss tonight isn't medical advice, and thankfully, it's not something you'll ever need to worry about in practice. Gravity isn't going anywhere, but exploring impossible scenarios often reveals the most beautiful truths about how our universe actually works. So take a deep breath, settle in, and let's imagine the impossible together. The thing about gravity is that we barely notice it until it's gone. Right now, as you listen to this, gravity is pressing you gently into your seat with a force equal to your entire body weight. It's pulling the blood in your veins downward, requiring your heart to work constantly against it. It's keeping the air molecules in your lungs from drifting away, maintaining the atmospheric pressure that allows you to breathe without thinking about it. Gravity is holding the water in your glass, the roof over your head, and every single atom of the atmosphere that surrounds our planet. It's the reason rain falls down instead of floating away, why rivers flow toward the sea, and why you don't have to worry about your morning coffee drifting off into space. But gravity is more than just a force that keeps things stuck to the ground. It's the invisible hand that shaped every biological system on Earth over billions of years. Your bones grew dense enough to support your weight against gravity's pull. Your inner ear developed intricate, fluid-filled canals specifically designed to detect which way is down in a gravitational field. Your cardiovascular system evolved to pump blood upward against gravity's relentless tug. In fact, gravity has been the one constant environmental factor throughout the entire history of life on Earth. While climates have shifted, continents have drifted, and extinction events have reshaped the tree of life, gravity has remained perfectly steady at 9.8 meters per second squared for the past 4 billion years. Every cell in your body, every instinct in your brain, every automatic function of your physiology has been fine-tuned by evolution to operate under this specific gravitational load. So what happens when that constant disappears? Let's begin with the first few seconds, because that's about how long you'd have to contemplate this new reality before things become, shall we say, considerably more complicated. The moment gravity vanishes, you would experience something no human being has ever felt in the entire history of our species. Not the gentle float of swimming, not the brief weightlessness of jumping off a diving board, but true, absolute weightlessness combined with the terrifying realization that the Earth itself is no longer holding you. The sensation would be immediate and unmistakable. every person on the planet would suddenly feel like they're falling, even though they're not falling at all. They're rising. The fluid in your inner ear, evolved over millions of years to detect gravitational orientation, would be thrown into complete chaos. Within moments, you'd be overwhelmed by the most severe motion sickness imaginable. The kind of nausea and disorientation that makes a roller coaster feel like a gentle rocking chair. But here's where it gets interesting from a physics perspective. Earth is spinning. Right now, as you sit there, you're moving at roughly 1,040 miles per hour if you're near the equator, slower if you're closer to the poles. Gravity is what keeps you moving along with the planet's rotation instead of flying off into space. It's providing what physicists call centripetal force, constantly pulling you inward to maintain your circular path around Earth's axis. Remove gravity, and suddenly that centripetal force is gone. You, along with everything else on Earth's surface, would begin moving in a straight line at whatever speed you were travelling when gravity disappeared. For most of us, that means we'd be launched tangentially from Earth's surface at hundreds of miles per hour. Imagine standing on a merry-go-round that's spinning rapidly. As long as you hold on, you rotate with it, let go, and you fly off in a straight line. That's essentially what would happen to every person, every animal, every loose object on Earth's surface the moment gravity stopped working. But you wouldn't be alone in this cosmic ejection. The atmosphere itself would begin its own journey into space. Those air molecules surrounding you, normally held close to Earth's surface, by gravitational attraction, would start drifting away. The atmospheric pressure that you've never consciously noticed would begin dropping immediately. And this is where things become truly catastrophic from a biological standpoint. Your body is exquisitely adapted to function under atmospheric pressure. The air pressure at sea level is about 14.7 pounds per square inch, pressing against every surface of your body. Your lungs, your blood vessels, even the cells in your tissues all rely on this pressure to maintain their structure and function properly. As the atmosphere begins to escape into space, that pressure would drop rapidly towards zero. Your eardrums would likely rupture from the sudden pressure change. The saliva on your tongue would begin to boil not from heat, but from the lack of pressure. This is the same phenomenon that causes water to boil at lower temperatures at high altitudes, except now the altitude is effectively infinite. Meanwhile, every body of water on Earth would begin its own spectacular departure. Oceans, lakes, rivers, even the morning dew on grass, every molecule of H2O would start floating upward in massive, shimmering globules. The sight would be breathtaking if you were in any condition to appreciate it. Picture the Pacific Ocean lifting off like some impossible liquid mountain range, carrying with it every whale, every fish, every microscopic organism that calls the sea home. The Amazon River rising like a serpentine ribbon of water stretching toward the sky. Every raindrop, every snowflake, every ice cube, in every freezer on the planet beginning its journey into the void. But water wouldn't remain liquid for long in the vacuum of space. Without atmospheric pressure, it would rapidly vaporize, turning into steam that would then disperse into the cosmos. The very substance that makes up roughly 60% of your body weight would begin to behave in ways that biological systems simply cannot tolerate. Now let's talk about what's happening inside your body during these first crucial minutes. Every cell in your body contains water, and that water is normally under pressure. Your blood vessels, your lymphatic system, even the individual cells that make up your organs, all rely on precise pressure relationships to function. As atmospheric pressure drops towards zero, the physics of cellular function begins to break down. The proteins that carry out the essential chemistry of life are exquisitely sensitive to their environment. They fold into precise three-dimensional shapes that allow them to perform their functions, and these shapes are maintained partly by the pressure and density of the surrounding fluid. Change that environment dramatically, and proteins begin to unfold or denature, losing their ability to do the work that keeps you alive. Your cardiovascular system, evolved over millions of years to pump blood against gravity's downward pull, would find itself in a completely alien environment. Without gravity to pool blood in your lower extremities, circulation patterns that have remained constant throughout human evolution would suddenly become chaotic and unpredictable. The heart muscle itself, which has never in the history of life on Earth had to function without gravitational loading, would be operating in completely uncharted physiological territory. Blood pressure, heart rate, the very rhythm of circulation that has beaten steadily in your chest since before you were born, all of it would be attempting to function in conditions that no biological system has ever encountered. But let's zoom out for a moment and consider what's happening to our planet itself. Earth isn't just a solid rock floating in space. It's a complex layered system held together by gravitational forces. The dense iron core at the centre creates immense pressure that keeps the layers above it compressed and stable. The rocky mantle, the thin crust we live on, all of it exists in its current form because gravity is constantly pulling every atom toward the planet's centre. Remove that gravitational binding force, and the Earth itself would begin to come apart. The internal pressure at Earth's core is roughly 360 gigapascals. That's about 3.6 million times the atmospheric pressure at sea level. This pressure exists because of the weight of all the rock and metal above, pressing down due to gravity. Without that downward pull, those internal pressures would have nothing to push against. Imagine a pressure cooker with the lid suddenly removed. The contents would explosively expand outward. Something similar, though far more dramatic, would happen to our planet. The rocky layers that make up Earth's structure would begin separating and expanding outward, no longer held together by gravitational compression. But even before the planet itself disintegrates, Earth's rotation would become a destructive force. Those crustal plates that form the continents, normally held in place by gravity, would begin lifting away from the mantle beneath. The spinning motion that gives us day and night would start tearing the planet apart as centrifugal forces overcome the gravitational binding that normally keeps everything together. Mountains would crumble not from earthquakes, but from the simple fact that their own mass would no longer be held down by gravitational force. Entire continents would begin breaking apart and drifting away from the planet's surface, carrying with them every tree, every building, every geological feature that took millions of years to form. And through all of this planetary disintegration, plant and animal life would be experiencing their own unique catastrophes. Plants, those quiet organisms we often take for granted, are actually exquisitely tuned to gravity's presence. They use gravitational cues to determine which direction is up and which is down. Roots grow downward, following gravity toward water and nutrients in the soil. Shoots and stems grow upward, against gravity, reaching towards sunlight. This process, called gravitropism, is so fundamental to plant biology that many species couldn't survive even brief periods without gravitational orientation. The cellular mechanisms that detect gravity and coordinate growth would be thrown into complete confusion. Even if plants could somehow survive in a gravity-free environment, their entire structural design is based on the assumption that gravity will always be pulling them downward. Trees, those magnificent organisms that can live for thousands of years are essentially gravity-defying structures. Their trunks and branches are engineered to support their weight against gravitational pull while remaining flexible enough to bend in the wind. Remove gravity, and their structural integrity becomes not just unnecessary, but potentially problematic as they're launched into space, along with everything else. Animals, meanwhile, would face immediate physiological challenges that go far beyond simply floating away. Every aspect of animal biology, from the smallest insect to the largest whale, has been shaped by the constant presence of gravitational force. Consider something as basic as balance. Your inner ear contains tiny calcium carbonate crystals, called otoliths, that rest on sensory hair cells. When you tilt your head, gravity pulls these crystals in different directions, bending the hair cells and sending signals to your brain about your orientation. Without gravity, these crystals would float freely, making it impossible for your brain to determine which way is up. But the effects go much deeper than balance and orientation. Bone density, muscle strength, even the thickness of your blood, all of these are calibrated for life under Earth's specific gravitational load. Astronauts who spend just a few months in the microgravity of space experience significant bone loss, muscle atrophy, and cardiovascular deconditioning. And that's in the carefully controlled environment of a space station, with exercise equipment and medical monitoring. In our gravity-free scenario, there would be no time for adaptation, no gradual adjustment. Every biological system would be instantly operating outside its evolved parameters. As we drift toward the end of this first part of our journey into gravitational catastrophe, it's worth pausing to appreciate just how much we normally take for granted. The simple act of sitting in a chair, of feeling solid ground beneath your feet, of knowing intuitively which direction is down. These aren't just conveniences, they're the fundamental assumptions upon which all life on Earth is built. Gravity isn't just a force that keeps us from floating away, it's the invisible architect of our entire reality, the silent constant that has shaped every aspect of existence on our planet for billions of years. Remove it, and we don't just lose our footing, we lose the very foundation of biological possibility itself. But our exploration is far from over. In the next part of this cosmic thought experiment, we'll delve deeper into what happens as Earth continues to disintegrate, how the absence of gravity affects the very atoms and molecules that make up matter, and why the consequences extend far beyond our planet to the stars themselves. The universe, it turns out, is far more delicately balanced than most of us realise. And sometimes, imagining what happens when that balance is broken can reveal the most profound truths about the reality we inhabit every single day. For now, let's continue our quiet journey through this impossible scenario, because there's so much more to discover about what happens when the fundamental forces of our universe simply stop working. As we drift deeper into this gravity-free world, something remarkable and terrifying begins to happen at the molecular level. You see, gravity doesn't just affect the big obvious things like planets and people. It influences the behaviour of matter itself, right down to the tiniest scales of existence. Inside every living cell, there's a delicate dance of molecules that has been choreographed by billions of years of evolution under constant gravitational influence. Proteins fold into their functional shapes, partly because of how gravity affects the distribution of mass within the cell. Ion channels, those microscopic gates that control the flow of charged particles across cell membranes, operate based on pressure gradients that assume a gravitational field will always be present. When gravity vanishes, these ion channels begin to behave erratically. Sodium, potassium, calcium, and other essential ions that normally flow in predictable patterns suddenly find themselves in an environment their cellular machinery was never designed to handle. The electrical signals that allow your neurons to communicate, the chemical gradients that power cellular metabolism, the very foundations of biochemistry itself, all of it begins to malfunction simultaneously. It's rather like watching a symphony orchestra where every musician is suddenly given a completely different piece of sheet music. The individual players might be talented, but the harmonious coordination that creates beautiful music dissolves into chaos. In your body, this chaos manifests as the rapid breakdown of every biological process that keeps you alive. But let's step back from the cellular catastrophe for a moment and consider something equally fascinating. What's happening to the weather? Weather, you see, is fundamentally a gravitational phenomenon. The reason we have wind, rain, storms, and all the atmospheric dynamics that shape our climate is because gravity creates density differences in the air. Cold, dense air sinks downward due to gravitational pull, while warm, less dense air rises upward. This constant circulation, driven by gravity and powered by solar energy, creates the weather patterns that have existed as long as Earth has had an atmosphere. Remove gravity, and weather simply stops existing. The swirling hurricane that might have been approaching a coastline would find its circular motion continuing, but without the density-driven circulation that gives it structure and power. The eye of the storm, that eerily calm centre, exists only because gravity allows dense air to spiral downward, while lighter air rises around it. In a gravity-free world, that elegant spiral would dissolve into formless atmospheric chaos. Rain, perhaps the most gravity-dependent weather phenomenon of all, becomes physically impossible. Those water droplets that normally fall from clouds due to gravitational attraction would instead float away into space along with the rest of the atmosphere. The water cycle that has nourished life on Earth for billions of years, the evaporation, condensation, and precipitation that moves moisture around our planet, would simply cease to function. Even the clouds themselves, those beautiful formations we watch drift across the sky, exist only because gravity allows water vapour to condense around microscopic particles and then remain suspended at specific altitudes where temperature and pressure conditions are just right. Without gravity to create those pressure layers, cloud formation becomes impossible. It's a strange thought, isn't it? That something as seemingly simple as the absence of a single force could erase every weather pattern, every climate system, every atmospheric phenomenon that has shaped the history of our planet. The gentle rain that waters your garden, the snow that blankets mountains in winter, the summer thunderstorms that cool hot evenings, all of it depends on gravity's invisible hand. Now, as our planet continues its disintegration in this impossible scenario, something even more dramatic begins to unfold. The geological processes that have shaped Earth's surface over millions of years suddenly find themselves operating in reverse. Volcanoes, those magnificent expressions of Earth's internal energy, would experience something unprecedented. The magma that normally rises through the crust due to buoyancy effects, gravity making the lighter, molten rock float upward through denser solid rock, would find itself in an environment where the concept of up no longer has meaning. Without gravitational pressure to keep the Earth's interior compressed and stable, the magma chambers that feed volcanic activity would begin expanding explosively outward. but instead of erupting upward through volcanic vents, this molten rock would expand in all directions simultaneously, no longer constrained by the weight of overlying rock. The tectonic plates that form Earth's surface, normally held in their slow grinding dance by gravitational forces, would begin separating and drifting apart at unprecedented speeds. The mid-ocean ridges where new oceanic crust is born, the subduction zones where old crust is recycled into the mantle, all of these geological processes depend on gravity to maintain the pressure gradients that drive plate tectonics. Mountains, those ancient monuments to geological forces, would face their own unique fate. The Himalayas, formed over millions of years by the collision of continental plates under immense gravitational pressure, would begin to literally fall apart. Not from erosion or weathering, but from the simple fact that the compressive forces that hold their rock layers together would no longer exist. Imagine watching Mount Everest, that iconic peak that has challenged human ambition for generations, simply coming apart like a house of cards. The limestone, granite, and metamorphic rocks that form its structure, normally compressed together under enormous pressure, would begin expanding and separating as the gravitational forces that created that pressure vanish. But perhaps the most poetic tragedy in this geological collapse would be the fate of Earth's great canyons and valleys. The Grand Canyon, carved over millions of years by the Colorado River, flowing downhill due to gravity's pull, would become a monument to forces that no longer exist. The river itself, of course, would have long since floated away into space, leaving behind only the sculpted stone testimony to gravity's patient artistry. As we contemplate these geological catastrophes, it's worth considering what's happening to the human structures we've built on Earth's surface. Our cities, our roads, our bridges, our homes, all of them were designed and constructed with the assumption that gravity would always be there to provide structural loading and keep everything firmly planted on the ground. Skyscrapers, those magnificent expressions of human engineering ambition, are essentially gravity-defying structures. They're designed to support their own weight against gravitational pull while remaining stable against wind forces. The deeper the foundation, the taller the building can safely be, because gravity helps anchor the structure to the bedrock below. Remove gravity, and these architectural marvels become elaborate projectiles. The Empire State Building, the Burj Khalifa, the countless towers that define our urban skylines would all begin their journey into space, no longer held down by their foundations or their own weight. But it's not just the tall buildings that would face immediate structural failure. Even simple houses rely on gravity in ways we rarely consider. The roof stays on because gravity pulls it down onto the walls. The walls remain vertical because gravity defines what down means. The foundation works because gravity presses the structure against the ground, creating friction that resists horizontal forces like wind. In a gravity-free environment, every human structure would essentially become space debris, drifting away from Earth's surface along with everything else that was once anchored by gravitational attraction. Transportation systems would face their own unique challenges. Automobiles, trains, ships, aircraft, all of them rely on gravity in fundamental ways. Cars stay on the road because gravity creates the downward force that generates friction between tyres and pavement. Remove that force and driving becomes impossible, not because the engine stops working, but because there's no way to maintain contact with the road surface. Trains, those marvels of efficient transportation, depend entirely on gravity to keep their wheels on the tracks. The enormous weight of a fully loaded freight train, pressing down on the rails due to gravitational force, is what allows the locomotive to generate enough friction to pull its cargo. Without gravity, even the most powerful train engine would simply spin its wheels uselessly while the entire train drifts away from the tracks. Ships present an interesting case study in gravitational dependence. They float because the gravitational force pulling them downward is exactly balanced by the buoyant force of the water pushing upward. This is Archimedes' principle in action, and it only works because gravity creates the pressure gradients in water that generate buoyant force. In a gravity-free ocean, if such a thing could exist, ships wouldn't float. They would simply drift through the water, as if it were a three-dimensional medium with no preferred direction. But of course, as we've already established, the oceans themselves would be floating away into space, making the entire question of maritime navigation rather academic. Aircraft, perhaps ironically, might initially seem less affected by the loss of gravity. After all, they're already defying gravity to some extent, using aerodynamic forces to generate lift. But airplane wings generate lift by creating pressure differences above and below the wing surface. And these pressure differences depend on the density of air, which is maintained by gravitational compression of the atmosphere. As the atmosphere expands and disperses into space, air density would drop rapidly, making aerodynamic flight impossible. Even if a pilot could somehow maintain control in the increasingly thin air, there would be nowhere to land, as airports and runways would be among the first infrastructure to float away from Earth's surface. But let's consider something even more fundamental than transportation or architecture. Let's think about time itself. This might seem like a strange tangent, but Einstein's theory of general relativity tells us that gravity and time are intimately connected. In regions of strong gravitational fields, time actually passes more slowly relative to regions of weaker gravitational fields. This gravitational time dilation is a fact, called measurable and real. GPS satellites have to account for it to maintain their accuracy. On Earth's surface, we experience a specific rate of time passage that's been constant throughout human history. Our biological clocks, our circadian rhythms, even our perception of duration have all evolved under this particular temporal environment created by Earth's gravitational field. Remove gravity and we remove the gravitational influence on space-time itself. The rate at which time passes would change, becoming uniform with the time experienced by objects in deep space far from any gravitational influence. This change would be subtle, too small for human perception, but it represents yet another way in which the loss of gravity would fundamentally alter the nature of existence itself. Our cellular processes, our neural activity, even our consciousness operate on timescales that have been calibrated over billions of years of evolution under Earth's specific gravitational time dilation. Would removing that influence affect the rate of biological processes? It's a question that touches on some of the deepest mysteries of physics and biology. As we near the end of this portion of our journey through gravitational catastrophe, I find myself thinking about something rather beautiful and melancholic. In this impossible scenario, as Earth disintegrates and all life drifts away into the cosmic void, there would be a brief moment when our planet's history becomes visible in a way it never has been before. All the water that has flowed in Earth's rivers, all the air that has carried the songs of birds and the voices of human beings, all the soil that has nourished countless generations of plants and animals. It would all be spreading outward into space in a vast, expanding sphere of matter and memory. For a few precious minutes before the cold of space and the vacuum of the void claimed everything, there would be this incredible dispersion of Earth's entire biosphere. Every raindrop that ever fell, every breath ever taken, every leaf that ever rustled in the wind, all of it moving together in a final unplanned exodus from the world that gave it birth. It's a strangely poetic end to 4.5 billion years of planetary evolution. All of Earth's history, from the first microscopic life forms to the great civilizations of humanity, spreading out into the darkness like some cosmic dandelion releasing its seeds to the stellar wind. But even this isn't the end of our story, because the effects of gravity's disappearance extend far beyond our small planet. The Sun itself, that massive nuclear furnace that has powered life on Earth since the beginning, would face its own catastrophic fate without gravity to hold it together. And that's where we'll continue our exploration next time, as we discover how the loss of gravity would unravel not just our world, but the very stars themselves, in ways that reveal the delicate balance upon which our entire universe depends. Sleep well tonight, knowing that gravity is there, quietly holding everything together, just as it always has been and always will be. Now, as we drift toward the most profound implications of our impossible scenario, we must turn our attention to the Sun itself. That brilliant sphere of nuclear fire that has warmed our faces and powered our dreams for billions of years would face a fate so spectacular, so utterly devastating, that it makes the destruction of Earth seem almost gentle by comparison. You see, the Sun is not simply a ball of hot gas floating in space. It's a precisely balanced battle between two of the universe's most fundamental forces. Nuclear fusion in its core generates an outward pressure so immense it could blow the Sun apart in minutes. Meanwhile, gravity provides an inward pull so relentless that it compresses the Sun's matter to densities and temperatures that would be impossible to achieve any other way. This balance is exquisite. For the past 4.6 billion years, these two forces have been locked in a perfect standoff that has kept our star burning steadily, converting hydrogen into helium at just the right rate to provide the energy that makes life on Earth possible. Remove gravity from this equation and the Sun would face what physicists call a catastrophic explosion. Without gravitational compression to contain it, the nuclear furnace at the Sun's core would suddenly find itself free to expand outward at incredible speeds. All that energy, normally held in check by the Sun's own gravitational field, would be released in a stellar explosion that would make the most violent supernova seem like a gentle firecracker. The Sun would quite literally blow itself apart, sending its entire mass streaming outward into the solar system at velocities that would carry solar material past the orbit of Pluto in a matter of hours. The light from this explosion would be visible from other star systems, a brief, brilliant flare announcing the death of the star that once nurtured a living world. But here's the truly mind-bending part about this cosmic catastrophe. It wouldn't just be our Sun facing this fate. Every star in our galaxy, every distant sun that twinkles in the night sky, would simultaneously experience the same gravitational collapse and explosive destruction. Imagine it. The entire Milky Way galaxy, home to hundreds of billions of stars, suddenly become a cosmic fireworks display of unprecedented scale. Red giants, white dwarfs, neutron stars, even the supermassive black hole at our galaxy's centre, all of them would face their own unique forms of gravitational catastrophe as the force that holds the universe together simply vanishes. The red giant stars, those ancient suns in the final stages of their lives, normally rely on gravity to maintain the delicate balance between their expanded outer layers and their dense cores. Without gravitational binding, these stellar giants would shed their outer atmospheres in spectacular displays of cosmic beauty, creating nebulae that would expand outward at unprecedented speeds. Neutron stars, those incredibly dense remnants of massive stellar explosions, exist only because gravity compresses matter to densities so extreme that atoms themselves are crushed out of existence. A teaspoon of neutron star material weighs about 6 billion tons, held together entirely by gravitational force. Remove that force, and these exotic objects would expand explosively, releasing energies that would dwarf even the most violent stellar explosions. And then there are the black holes themselves, those mysterious regions where gravity is so strong that not even light can escape. Black holes are, in a very real sense, pure gravitational phenomena. They exist as tears in the fabric of space-time itself, created by gravity so intense that it warps reality around them. What happens to a black hole when gravity disappears? This is where we enter territory that even our most advanced physics can only speculate about. The event horizon, that point of no return around a black hole, exists only because of gravitational effects. The singularity at its centre, where matter is compressed to infinite density, is held in that state entirely by gravitational collapse. Remove gravity, and these cosmic monsters would face something unprecedented in the history of the universe. The matter trapped within them, compressed beyond our ability to comprehend, would suddenly find itself free from gravitational constraint. The result would likely be an explosion, so violent, so energetic, that it would release more energy in seconds than our sun produces in billions of years. But let's zoom out even further, beyond individual stars and black holes, to consider what's happening to the large-scale structure of the universe itself. Galaxies, those magnificent spiral and elliptical formations that contain billions of stars, are held together by gravity. The beautiful spiral arms of the Milky Way, the elegant elliptical shapes of distant galaxies, even the dark matter halos that surround them, all of these structures exist only because gravity provides the binding force necessary to keep billions of stars moving together through space. Without gravity, every galaxy in the universe would begin to disperse. The stars that have been travelling together for billions of years, following ancient orbital patterns around galactic centres, would suddenly find themselves moving in straight lines, no longer bound by the gravitational wells that define galactic structure. Our own Milky Way, that vast pinwheel of stars that has been our cosmic home since the universe was young, would begin to unravel like a clock spring suddenly released from tension. The sun, along with hundreds of billions of other stars, would streak away from the galactic centre in perfectly straight lines, each following whatever trajectory it happened to be on when gravity disappeared. The Andromeda Galaxy, currently approaching the Milky Way for a collision billions of years in the future, would no longer be approaching at all. Instead, its stars would disperse into the cosmic void, following their own individual paths through space. The gravitational dance between galaxies that has shaped the evolution of the universe for over 13 billion years would simply cease to exist. Even the galaxy clusters, those vast congregations of hundreds or thousands of galaxies bound together by gravity, would dissolve into chaos. The Virgo cluster, the Coma cluster, the massive galactic superclusters that define the large-scale structure of the universe, all of them would begin dispersing as their constituent galaxies stream away from each other in all directions. But perhaps the most profound effect would be on the universe's ability to form new structures. You see, gravity isn't just responsible for holding existing structures together, it's also the force that allows new structures to form in the first place. Star formation occurs when clouds of gas and dust collapse under their own gravitational attraction, becoming dense enough and hot enough for nuclear fusion to begin. Planet formation happens when rocky debris in stellar disks gradually clumps together under gravitational influence, growing from tiny particles into massive worlds over millions of years. Even the formation of the first galaxies in the early universe required gravity to amplify tiny density fluctuations in the cosmic microwave background, allowing matter to clump together into the structures we see today. Remove gravity, and the universe would lose its ability to create new complexity. No new stars would ever form. No new planets would coalesce from cosmic dust. The universe would become a slowly expanding, cooling collection of individual particles, each following its own straight-line trajectory through an increasingly empty cosmos. It's a strangely melancholic vision, a universe that gradually becomes simpler rather than more complex, where the beautiful structures we see today represent the final flowering of cosmic creativity before everything disperses into eternal, unchanging motion. But let's return our attention to something more immediate and personal. What would be happening to human consciousness during these final moments of gravitational existence? The human brain, that remarkable 3-pound universe that generates your thoughts, memories, and sense of self, operates through incredibly complex patterns of electrical and chemical activity. Neurons communicate through precisely timed electrical impulses. Neurotransmitters cross synaptic gaps in carefully regulated concentrations, and the entire system maintains its function through delicate pressure and flow relationships that assume a gravitational environment. As atmospheric pressure drops towards zero and the cellular chaos we described earlier intensifies, your brain would be attempting to function in conditions that no nervous system in the history of Earth has ever encountered. The blood-brain barrier, that selective filter that protects your neural tissue from harmful substances, relies on pressure gradients maintained by cardiovascular function under gravitational influence. Without gravity, blood flow to the brain would become erratic and unpredictable. The cerebrospinal fluid that cushions your brain and spinal cord, normally circulating in patterns established by gravitational pressure differences, would begin behaving in completely unprecedented ways. What would consciousness feel like in those final moments? Would you experience the dissolution of gravitational reality as a gradual fading of awareness, or would there be moments of startling clarity as your brain attempts to process sensory input that no human nervous system was ever designed to interpret? Perhaps there would be a strange kind of peace in those last seconds, as the constant background stress of maintaining biological function against gravitational resistance suddenly disappears. For just a moment, before the cellular chaos becomes overwhelming, you might experience a weightlessness unlike anything any human has ever felt, a true freedom from the gravitational bonds that have defined every moment of human existence since our species first stood upright on the African savanna. Of course, this is all speculation. The reality is that consciousness itself may be more dependent on gravitational conditions than we currently understand. The quantum processes that some researchers believe underlie conscious experience operate in ways that could be profoundly affected by changes in the fundamental forces of physics. But even as we contemplate the end of human awareness, it's worth considering what this impossible scenario reveals about the nature of existence itself. Every thought you've ever had, every emotion you've ever felt, every memory that makes you who you are, has occurred in the presence of Earth's gravitational field. Your neurons have never fired without gravity's influence. Your synapses have never transmitted signals in a gravity-free environment. Your entire sense of self, your consciousness, your very identity has been shaped by 4 billion years of evolution under constant gravitational loading. In a very real sense, gravity isn't just something that affects you, it's part of what makes you possible. Remove it, and you don't just lose your physical form, you lose the environmental conditions that allow your consciousness to exist in the first place. As we near the end of our exploration of this impossible catastrophe, it's worth stepping back to appreciate the profound interconnectedness that this thought experiment reveals. The force that keeps your feet on the ground is the same force that keeps the sun burning, the planets in their orbits, and the galaxies spinning through space. Gravity connects the quantum scale to the cosmic scale, linking the behavior of subatomic particles to the evolution of the universe itself. It's the thread that weaves together every level of reality, from the molecules in your cells to the superclusters of galaxies that define the larger structures in the cosmos. This is perhaps the most beautiful lesson of our imaginary catastrophe, that we exist in a universe where everything is connected, where the same fundamental forces that govern the behavior of distant stars also regulate the beating of your heart and the firing of your neurons. The gentle pressure you feel as gravity holds you in your chair is not separate from the nuclear fusion occurring in the sun's core. The weight of your body is not disconnected from the orbital dance of planets or the spiral arms of distant galaxies. We are all part of the same gravitational symphony, playing out across scales of space and time that span from the infinitesimally small to the unimaginably vast. And in this cosmic orchestra, gravity serves as both the conductor and the stage, organizing matter and energy into the beautiful, complex structures that make existence possible. From the delicate architecture of DNA to the majestic spirals of galaxies, everything we know and love exists only because gravity provides the organizing principle that allows complexity to emerge from chaos. So as we drift toward the conclusion of this impossible journey, take a moment to feel the gentle pull of gravity holding you safely in place. Feel the weight of your body, the pressure of air in your lungs, the solid ground beneath your feet. These aren't just physical sensations, they're reminders of your place in the cosmic order, your connection to forces that have been shaping the universe for over 13 billion years. Tomorrow, when you wake up and take your first breath of the morning air, when you feel your feet touch the floor and experience the familiar tug of gravity orienting you to the world, remember that you're participating in the same fundamental physics that lights the stars and shapes the cosmos. Gravity will be there, as it always has been and always will be, quietly holding everything together in its invisible embrace. And in that constancy, that reliable presence of forces beyond our control or understanding, there's a kind of cosmic comfort that connects us to something far larger than ourselves. But our exploration of cosmic catastrophes is far from over. If you found this journey through gravitational impossibility both fascinating and unsettling, you might be interested in learning about real cosmic threats that exist right now in our universe. There are stars out there, massive stellar time bombs that could explode at any moment, sending devastating radiation across interstellar distances. The next time we meet, we'll explore a very real and present danger, the possibility that a nearby star could explode tomorrow, bathing Earth in deadly gamma rays. This star could explode any second. Is Earth next? Because sometimes reality is far more dramatic than any thought experiment we could imagine. Until then, sleep well in the gentle embrace of gravity, knowing that the forces that govern our universe are working exactly as they should, keeping you safe and sound in your cosmic home. But as we continue our gentle drift through this impossible scenario, something even more profound begins to emerge from the cosmic wreckage. You see, the disappearance of gravity wouldn't just destroy the structures. We can see it would fundamentally alter the very nature of matter itself at the most basic level. Deep within every atom that makes up your body, gravity plays a role so subtle, so seemingly insignificant, that most people never consider it. Yet even at the scale of protons and neutrons, gravitational effects contribute to the delicate balance that keeps atomic nuclei stable. It's an influence so tiny compared to the electromagnetic and nuclear forces that physicists often ignore it in their calculations. But in our impossible world, even these microscopic gravitational contributions would vanish. The result would be a universe where the fundamental constants of physics begin to shift in ways that no living thing has ever experienced. The binding energies that hold atomic nuclei together, the electron shells that determine chemical properties, even the quantum mechanical processes that govern how particles interact, all of these would find themselves operating in a subtly but significantly altered reality. It's rather like watching a master musician suddenly forced to play a familiar symphony on an instrument that's been tuned just slightly differently. The melody might still be recognizable, but every note would sound wrong, every harmony would be off-key, until eventually the entire performance dissolves into discord. In the atoms that make up your body, this quantum-level chaos would manifest as a breakdown in the chemical bonds that hold molecules together, the proteins that carry out the work of life, the DNA that stores your genetic information, even the simple water molecules that make up most of your mass. All of them would begin to behave in ways that biological systems simply cannot tolerate. But let's zoom out from the atomic scale to consider something that might seem unrelated but is actually intimately connected: the fate of information itself in our gravity-free universe. Every memory you've ever formed, every thought you've ever had, every piece of information that has ever existed on Earth is encoded in physical structures. Your memories exist as patterns of connections between neurons. Human knowledge is stored in the molecular structure of DNA, in the magnetic domains of hard drives, in the ink patterns on paper, in the quantum states of computer processors. All of these information storage systems rely directly or indirectly on gravitational stability. The paper in books stays flat because gravity pulls it down against the pages beneath. The magnetic domains in hard drives maintain their orientation, partly because gravitational forces help stabilize the physical structure of the storage medium. Even the neurons in your brain maintain their delicate architecture through processes that assume a constant gravitational environment. As Earth disintegrates and all these physical structures are scattered into space, something unprecedented happens: the complete destruction of an entire planet's accumulated information. Every book ever written, every song ever recorded, every photograph ever taken, every digital file ever created, all of it dispersing into the cosmic void, along with the physical media that contained it. It's a loss so profound that it transcends the merely physical. We're talking about the erasure of 4 billion years of evolutionary information, the entire genetic library of Earth's biosphere, and the complete cultural and intellectual heritage of human civilization, all vanishing simultaneously into the darkness between stars. This brings us to a rather melancholic realization about the nature of knowledge and memory. We often think of information as something abstract, something that exists independently of its physical substrate. But in reality, every bit of information requires matter and energy to exist. Every memory needs neurons, every book needs paper or digital storage, every song needs some physical medium to preserve it. In our gravity-free catastrophe, we're witnessing the ultimate demonstration that information and matter are inseparably linked. The love letters you've saved, the family photographs that capture precious moments, the scientific discoveries that have advanced human understanding, all of them are, in the end, patterns of matter that depend on gravitational stability for their continued existence. But even as we contemplate this cosmic erasure of memory and meaning, something beautiful begins to happen in the expanding sphere of Earth's dispersed matter. For a brief time, perhaps just hours or days before the cold of space claims everything, all the atoms that once made up our living world would be travelling together through the void. The carbon atom that was once part of a tree in an ancient forest would be drifting alongside the oxygen that once filled your lungs. The iron that once flowed in your blood would be sharing space with the calcium that once formed your bones. The hydrogen that once sparkled in dewdrops on morning grass would be moving through the darkness beside the nitrogen that once carried the calls of birds through summer air. In this strange dispersal, there would be a kind of cosmic democracy of matter. The atoms that once distinguished between living and non-living, between human and animal, between earth and sky, would all be equal participants in the same slow journey into interstellar space. The material that once formed Mozart's brain would be indistinguishable from the material that once formed the keys of his piano, all of it sharing the same fate in the expanding sphere of Earth's final breath. This brings us to one of the most profound philosophical implications of our impossible scenario, the question of whether meaning can exist without stable physical structures to support it. Throughout human history, we found comfort in the idea that our actions, our creations, our love for each other might somehow persist beyond our individual lifetimes. We build monuments, write books, create art, and raise children partly because we hope that something of what we are will continue after we're gone. We find meaning in the thought that we're part of something larger than ourselves, something that connects us to past and future generations. And so we come to the end of our impossible journey through a universe without gravity, a thought experiment that reveals the profound interconnectedness of everything we know and love. What began as a simple question about the disappearance of a single force has led us through the complete unravelling of reality itself, from the cellular chaos in our bodies to the explosive death of stars across the cosmos. Perhaps the most beautiful truth this catastrophe reveals is how exquisitely balanced our existence really is. Every breath you take, every heartbeat, every moment of consciousness depends on forces so fundamental that we rarely pause to acknowledge them. The gentle weight pressing you into your chair right now isn't just physics, it's the invisible foundation upon which all life, all meaning, all possibility rests. In imagining gravity's absence, we've discovered its true presence in every aspect of our being. It shapes not just our bodies but our thoughts, not just our planet but our place in the cosmic order. We are, quite literally, children of gravity, sculpted by billions of years of its patient influence into beings capable of contemplating our own existence. Tonight, as you drift towards sleep, feel that familiar tug holding you safely to the earth. Let it remind you that you're part of something vast and ancient and beautiful, a universe where the same forces that birth stars also cradle you in their invisible embrace. Gravity will be there when you wake, as constant as it has been for 4 billion years, quietly holding everything together in perfect eternal balance. If tonight's journey through cosmic impossibility has stirred your curiosity about the real dangers lurking in our universe, join me next time as we explore a very present threat that could change everything. This star could explode any second. Is Earth next? Because sometimes the most terrifying scenarios aren't impossible at all. Until then, sleep well in gravity's gentle hold, knowing you're exactly where you belong in this vast interconnected cosmos we call home. Cosmos we call home.